Hello everyone, my name is Michael Cubeddu, co-founder and head of research and development at Aliro Quantum. We are the quantum networking company. Fun fact, we were actually the first vendor to sign up for a booth at Quantum World Congress, so we've been here since the get-go. Really exciting to see how the whole industry has developed over the years. Really great engagement across quantum computing, networking, and sensing. We absolutely love this conference, a great mix of end users, ecosystem partners, and academics and students eager to learn more. So today I'm going to be talking about a full stack BBM92 quantum network. And those of you who have heard BBM92 before or have not, the key point I want to make here is that this is a quantum secure communications network that is based on the principles of entanglement. And now quantum networks, there are many different ways to design them. I'll talk a little bit about that. But you can view entanglement distributed over a network as really a useful resource upon which so many applications can really thrive. In this case, I'll be talking about a specific protocol, BBM92, for key distribution. Now, before I get into BBM92 specifically and how we've constructed a quantum secure communications network, I did want to kind of step back and take a look at how quantum networking technology has evolved over the years since we've been in the space, and I think is well reflected by the success of this conference, the messaging, the awareness around quantum networking in general. And really, the point I wanted to make with this slide is we've seen a massive uptick in probably the last 12, 18 months or so of increased demand for entanglement technology, for quantum networks based on entanglement and quantum interconnects as well. So on the top right there, you see a snapshot, not comprehensive by any means, but a snapshot of all the test beds, all of the quantum network activities that are happening here domestically. Of course, there are many other test beds around the world. But really, over the past few years, we've seen the development of quantum network testbeds really increase, and studying a variety of applications in security, in sensing, and entanglement itself to better understand it, how to better distribute it reliably over network infrastructure. We've also seen an uptick in quantum networking as really a way to encourage regional development, for economic development, for workforce development, for establishing this consortia of academic, industry, and government partnerships to really move the field forward. Most notably, I think, especially in the last year or so, we're seeing huge investments from the quantum computing space into quantum networking. And I think that's a key signal for the quantum networking industry and the quantum industry as a whole. Vendors around the world realize that we cannot scale to fully fault-tolerant utility-scale systems without networks, right? This is the same trend that happened in classical HPC. We cannot build monolithic systems. We network together a bunch of smaller processors. Same principle applies to quantum, okay? Finally, the last trend I think is worth talking about and gaining more notoriety is the so-called quantum space race, okay? We're really seeing an uptick in the development of satellite infrastructure, adapting existing free space optical systems to quantum. And this is motivated partly by China's advancements in quantum satellite infrastructure, their demonstrations, but also viewing quantum satellites as an alternative to potentially undersea cable infrastructure and things of that nature. Okay, so I mentioned at the top that entanglement is a resource, right, upon which all of these applications, quantum computing included, can really rely on. So here I'm going to dial in on secure communications. Now this is the application of quantum networking that is here today. These are applications and networks that we can build and deliver in production-grade settings for security. Now, all these other applications, quantum satellites, networking, quantum computers, distributed quantum sensing, will evolve over time. So what we're focused on is really building the stack to support the use cases today in security, but with the anticipation that all of these amazing distributed quantum applications will arise over the years as hardware matures, as applications are better understood, right? Okay, so dialing in on security, If you've heard of the quantum safe ecosystem, there are many different solutions out there. It can be somewhat confusing to kind of break down what exists today, what exists in the future, and how can I, as an enterprise or as an agency, as a large organization, looking to be quantum ready, to be quantum safe from the threats posed by quantum computing. There are many solutions out there. Now, there are two broad classes of quantum safe solutions, one based on math and the other based on physics. Okay, so in the math-based encryption algorithms, we're moving away from legacy encryption, RSA, elliptic curve cryptography. Our encryption, our digital infrastructure has relied on these math problems that we thought would last the test of time, right? The prime factoring problem, the discrete logarithm problem. And they did last us, quite a bit of time, and we use them every day for security. However, we know that they are vulnerable to attack by quantum computers. So we need to move away from those legacy math problems and adopt new techniques. Now, the question is, how do we best adjust for the quantum threats? So one option is to update those older math problems with new math problems that we hope will be quantum safe. In fact, they are quantum resistant, we hope, right? But there's no proof to say, oh, this new math problem will stand the test of time for infinity and for all future computing systems. But that being said, it's math-based. We know how to implement it on existing technology. There's nothing really quantum about it. It's a software update that is very complex, don't get me wrong. Many enterprises are going through this migration to start the process of becoming quantum safe. Then the other two at the top are physics-based solutions. They actually use the principles of quantum mechanics, superposition, entanglement, using quantum to protect from quantum. Okay? And these are known as quantum key distribution and quantum secure communications. And what we focus on is the top one there, which is entanglement-based quantum key distribution. Okay, so now getting into what this network actually looks like. How do we use entanglement, distribute it, and do something useful with it for security, right? So there are many layers that go into this, and at the bottom, this is all about the quantum hardware itself, right? Specialized components to generate entanglement at a very high rate, put them on fiber, so we have flying qubits, optical signals going from our entanglement sources to our end nodes. We have measurement apparatuses to actually detect those photons, to measure them in the right way, in a way that can turn single photons and entangled pairs of photons into keys that today's infrastructure can really leverage for security. So there are many steps that go on in that process. And one critical layer there in red is what we call the link layer. Okay, this is responsible for doing all of the real-time control that we need to figure out, okay, when did my photons arrive here and there? Were these photons in fact entangled? How did I measure those photons? And you're turning these photon clicks into something that is secure, a key that we can confidently say is secret to Alice and Bob, and it's not known to any eavesdropper. And then we have existing infrastructure, okay? As a field, we can't make the case that, okay, quantum networking is great, has all these amazing applications, but we need to lay down new special quantum fiber. That's never gonna happen. This technology will not be adopted, okay? We need to coexist with what is there today. There are plenty of routers and switches and classical networking gear. There's fiber that has been laid in the ground for decades. We need to leverage what is there today in order for this technology to be adopted. So what we need is product integrations with existing technology. So networking gear, these are encryptors that do very high throughput communications, and they're hungry for keys. We need to feed them the encryption keys. And that's all the quantum network is doing. You can think of it as an underlay. So we're delivering the keys. In this case, we worked with Cisco to deliver those keys and integrate with their routers and switches. And we established a VPN based on IPsec, a very well-known, widely used protocol for encryption. And we feed them with 256-bit keys. So from the classical network perspective, all we're doing is changing where you're getting your keys from. And by that, you can be quantum safe. Now, designing this kind of network is not easy. Quantum signals are very fragile. They change, even in a small chip in quantum computing, there are many issues we deal with noise, coherence, all of that. Same applies to quantum networking. Now it's at scale. right? We have distributed quantum states over a long distance. Fiber is unstable. We need to think about, how do we design the link to be stable, the network to be reliable? How do we have observability into the network itself, what's going on? And so for this, we've used our simulator to help design, okay, what hardware components out there work together? What performance can I expect? And then we also used digital twins and emulations to see, okay, what kind of timing synchronization do I need between these nodes? How can I solve some of these edge cases to make sure the network is up and running? So taking a step back again, I wanted to kind of position ourselves within the quantum networking ecosystem. Quantum networks can have applications across all these use cases that I mentioned in security, in computing, and in sensing as well. So what we're focused on is the software stack to enable these applications. And we're designing these layers, that link layer, that orchestration layer, to make sure that we can support things like key distribution today, but also support networks of quantum computers and quantum sensors in the future. To do that, we rely on robust partnerships with the ecosystem. And this week, we've announced over 50 devices integrated into our software stack. These are components across the field in quantum optics, so photon sources, detectors, optical switches, everything in between that you would typically find in a quantum network. There's no one way to build a quantum network. There are many different qubit modalities, similar to the quantum computing space. There are different wavelengths by which we can encode our qubits, different degrees of freedom in the photons, if it's polarization, if it's time-bend, many different ways to actually build a qubit and send those qubits around a network. But the point is here, the physical layer, the hardware space, is moving rapidly. There are many different vendors and approaches, all with unique pros and cons. And so through these integrations, we can actually design the networks for the customer use case, for the topology they're looking for the performance metrics they need to be successful, right? And at the top, with this software stack, we can support all these different applications as they emerge. So some takeaways here. We need to make the case that entanglement-based networking can coexist with today's infrastructure. We cannot have quantum networking be an isolated, expensive infrastructure redevelopment. We need to coexist with networking and fiber infrastructure that is here today. Okay. We enable security services, but also network management and scalability. This is a fast-moving field, especially in quantum networking, with all the recent advancements and investments. Scalability is key, right? We can support, certain metropolitan regions, as I showed in that map, but over time, right, we need to connect these networks. If you look at that map, and you look at a map of ARPANET, the evolution of the internet, how we got here, very similar trends. Okay, we started with local area networks, we went to metro regions, started to connect them, and then we found applications. No one was thinking about Google, Facebook, YouTube when we started building ARPANET. So we're trying to kind of replicate those trends, build in security from the get-go rather than an add-on, kind of like the internet was. So let's take the lessons learned from the internet, make sure this technology can scale, that these vendors can interoperate, that we know how to best create these links reliably to scale this technology beyond the metro region, to support satellites, to support quantum repeaters, support all these different use cases. We heard a lot about supercomputing. How are QPUs going to integrate with HPC infrastructure? There's a lot of migration and redesign going on of data center infrastructure, of network security. This is the arena which we're all playing. And so, design, validation, piloting is critical to make sure this technology can scale going forward. So thanks again for listening. Feel free to reach out. We have some great educational resources as well. I promise you they will be less salesy than this presentation was. But if you're interested in learning more about quantum networks, we have a wide range of topics there and videos and white papers as well, everything from what is a quantum network, what is a qubit, to how do I deploy a quantum satellite infrastructure? How do I integrate this into IPsec? These kinds of topics. So please reach out, take a look at our material, and stop by our booth.